No. So let's resume the session now. Our next speaker is Rajarama Bhat, who we all call as Raja. He's going to speak on Bures distance for completely positive maps.
Okay, so anyway, birthday wishes to Sundar. I'm very happy to be here, and thanks to Vijay. So, yeah, this is the pointer, right? And this is okay. Yeah, so I first met Sundar in a workshop in Hyderabad, actually. So I was a student in Delhi, and he was in Bangalore, and he spoke about GNS construction and things like that, so he introduced me to sister algebras really. And I remember he asking me to take some tutorial on this continuous functions on 0, 1 ideals and that, and also telling later about this factors, the isomorphism problem for free group factors and things like that. And so I said it should not be too difficult, but of course I'm much wiser now. So, and sometime later I had gone to Bangalore, and he gave me some problem about CP maps, the same thing what I'm talking about when I said that I'm working on completely positive maps. So he gave me a conjecture, and I could find some counterexample in higher dimensions, and I came to know that he and Pati meanwhile had solved it proved it in affirmative for 2 dimensions. It is, I think it's an interesting problem. It's about this doubly stochastic matrices. You may have heard this Birkhoff-Feynman theorem, which says that for doubly stochastic matrices, the permutations are the extreme points. Okay? So similar thing in a non-commutative context for CP maps. What are the extreme points, whether they are automorphisms? And it is true in 2 dimensions, but not in higher dimensions. And that is the only joint paper I have with Sundar and Pati it is. So then I went abroad, and when I came back, he had left Bangalore. I came back to Bangalore, and he had just left Bangalore to Chennai, so unfortunately. And but the good thing about that was that I got the quarters vacated by him, and I also got some 1 jacaranda tree and 3 avocado trees. So we still have them, and it's nice. And I also would like to thank. Yeah, I also would like to thank him for the number of workshops he has been holding here. Me and my students have benefited a lot from them. Okay, so let me come to the subject now. So I will be talking about the CP map. So this is actually I came to know that I have to use this. I cannot really use the blackboard here only just yesterday, so I had to type out everything yesterday night, and there could be many mistakes. So so right in the beginning, let me put the acknowledgements. It's a joint work with my student Sumesh, and I also would like to thank KBS and Ramesh for many discussions we had. And as I said, this is just work in progress, so there are many loose ends. Okay, so let me go to what it is. I see it's a really mixed audience here, so I think I got to start from real basics. And the basics is the C-star algebra theory. The C-star algebra theory starts with the states, and so you take unital C-star algebra. So if you don't know what C-star algebras are, you can think of them as n cross n matrices or operators, the space of the collection of operators on a Hilbert space, or even the space of continuous functions on a space. They also behave like C-star algebra, means on say continuous functions on a compact space. That's a C-star algebra. Okay. A unital C-star algebra, so that means it has a unit identity. And phi will take a state from on a C-star algebra. So now state means it's a positive linear functional. So it sends any C-star algebra has the positive elements, the elements of the kind x star x. So it sends positive things to positive things and sends the identity to identity. Okay. Of course, C is a C-star algebra, and then the GNS theorem says that there is a triple H pi Z. Okay. So it tells you that given this state, I can get this triple where this H is a Hilbert space. Okay. I am still trying to figure out how to use this. Okay. And a representation of the algebra. So that is a star homomorphism from A to B of H. And a vector. Okay. So I will get a unit vector here in this context, and such that the state phi of A is given by this element. So pi of A, the representation acting on Z in a product with Z. So it is like taking a diagonal entry of a matrix. So if you have the algebra of all matrices, if you just take a diagonal entry, say the first diagonal entry, so that is a state. So the theorem is saying that any state is of that kind. Okay, and okay, but it's more important here. It's not characterization of the state. It's a thing works nicely because the GNS theorem says that given a C-star algebra like this, which may not be given a priori as operators on a Hilbert space, so it could be like the space of continuous functions. It says that you can represent it in B of H. Okay, so I have not said one-to-oneness or anything here, but that will come later in the GNS theory. But the main point is that starting with states, one can get representations of the algebra. So you can finally embed this C-star algebra as an algebra of operators on a Hilbert space. That is the idea. And so there is also a minimality condition or uniqueness condition. So this GNS representation, this is called the GNS triple or the GNS representation. So that is unique up to unitary equivalence. If you put an additional condition here, namely this Hilbert space is spanned by these elements, by the action of this representation on this GNS vector or this vector span closure, that should be whole of H. So if you put that, then the triple is unique up to unitary equivalence. Okay, this is I think in C-star algebra theory, sort of you start with this GNS construction. Okay. Okay. So now suppose we have two states on the C-star algebra, say phi 1 and phi 2. Okay, and you try to do this kind of GNS construction, and question is if phi 1 and phi 2 are close, can we make the GNS representation, the representations which we get as close? Okay, so phi 1 and phi 2 are states, so they have a norm, just a positive linear functional, so you can just take the usual norm of phi 1 minus phi 2, and if they are close, can we say that the representations are close? Now it is difficult to make sense of that, because the representations are on different Hilbert spaces, say H1 and H2, and you have the representations themselves are different. Okay, and we have different vectors there. So what do we mean by they are close? Okay, so the idea is to look at common representations. So that is a representation on the same space, and the same space H as well as the pi also same. Okay, only the vectors are different. Okay, and then you can talk about the norm of Z1 minus Z2. So that is why here you cannot insist on the minimality. What we had in the GNS, we said that there is a unique GNS minimal representation. But here, when I look at two states, phi 1 and phi 2, I may not get the same representation. So I may have to go to different representations. So, but I would like to have a common representation to talk about the distance. So what we do, we take this kind of common representations, but the vectors are different. Okay, and then we see whether we can put the vectors close by. Okay, first question which comes is there any common representation? Okay, given two states, can we get a common representation? Well, you can, and all you have to do is take the direct sum. You take H1 direct sum H. So if you have two representations for phi 1 and phi 2, one for phi 1 and another for phi 2, just take the direct sum and take the direct sum of the vectors. That way you have a common representation. So common representation is always there. Okay. So then we have the definition of Bures distance. Suppose we have two states like this. So using this idea, you take the beta of phi 1 phi 2 is the infimum. of all such things, norm of Z1, Z minus Z2, where the infimum is taken over all common representations of phi1 and phi2. Okay. So a priori it is not clear how this infimum behaves. So well, whenever I say common representation, I mean this. The phi of 1 IA is Zi, phi A, Zi. So Z1 gives you phi1 and Z2 gives phi2. Okay. And this was considered by Bures long time ago, actually, 60s, I think. What happens? He did show that this beta is a metric, and it's actually attained. The infimum is attained, not just that. So again, the idea is to take a sort of universal representation. You can take the representations of all these phi states, and you take their direct sum, and that kind of thing you can do. And then there is a compactness argument to show that the infimum is attained. And moreover, you get an inequality, an upper bound. Okay, beta is bounded by the square root of the usual norm. Okay, sorry. Okay. Okay. And surprising thing is that the infimum is attained in every common representation. I mean, though for initial thing one goes to all the direct sum and everything, but later on it was shown that it's actually attained in every common representation. Any common representation you can take, and there you can take the infimum. So in particular, you can take the direct sum. Okay. So now what I want to do, we want to go to the next level. Instead of states, we look at completely positive maps. That's the same thing which I was talking before. Here is the definition, one way of defining it. So you have a map now from the C-star algebra, not to the complex numbers, but to another C-star algebra. So it's completely positive if this inequality is satisfied for every tuple A1, A2, An in A, and B1, B2, Bn in B, any n. So any finite number of things. So if I had just one of them, then it would say that phi of, say, A star A is positive. So in particular, any completely positive map is positive, but it's more than that. So it is another way of putting it is that phi of matrices with entries from A is, if there also it is positive. Okay. So I will not go deeper into this, to the definition, but you just need to know that it's a generalization of positivity. And we also know that like star homomorphisms are positive, completely positive. Positive linear functionals, which I said, it is a generalization. The positive linear functionals are also completely positive. And if you do the natural operations like composition, sums, convex combinations of CP maps are all completely positive. Okay, they all retain the structure. And these are really very important maps, and I think for two aspects, I would say. One is for understanding C-star algebras, and I think this importance of the CP maps was realized very early on by Arvesen. So even in his basic papers on subalgebras, C-star algebras. And there are various concepts like nuclear C-star algebras and various things. Everywhere there you see that this notion of complete positivity is very important, and that is used. You see, what happens is that between C-star algebras, often there may not be any homomorphism. Like you take, say, matrix algebras, say Mn and Mm. If n and m are not compatible, there may not be any homomorphism. But you can always find completely positive maps. Okay, and so that way it helps. So to understand the C-star algebra, the structure of C-star algebras themselves. So the other thing is that is from the applications point of view. Also, these are very important. So you had seen in Rajiv Karandikar and also Shiva these semi-groups of positive things, which appear to understand Markov processes, the semi-group of positive maps. So you had the heat semi-group, for example. So the similar thing, if you want for in the non-commutative context, one of the natural candidates is these semi-groups of completely positive maps. Okay, instead of positivity, you need complete positivity. That's all. So you look at their semi-groups. They are the Markov semi-groups. Okay, the equivalents of heat semi-groups. So for that reason, this is important. So so they are supposed to describe what we call the quantum open systems. Okay, the systems which are where there is a decay or irreversibility. Okay, so that's old story. And then there are more recently people have found in this quantum information theory, quantum computations, they have things called quantum channels, and they are nothing but these CP maps. So various applications you see that you need these CP maps. Okay, so but for everything that makes it work about CP maps is this thing, I think, the Stinespring's theorem, which connects the CP maps to homomorphisms. Okay, and so given a completely positive map, so here I have made a choice. It is not going from A to B, but B of G, bounded operators on some Hilbert space. Okay, so this is the way usually the Stinespring's theorem is stated. So you have a CP map from the one C-star algebra A to bounded operators on some Hilbert space. Then there exists a triple, now H pi V, where H is a Hilbert space. Okay, and pi is a representation from A to B of H, and V is a linear map, bounded linear map from G to H, and phi of A is given like this, V star pi A V, for all A belongs to A. So the comparison with GNS cannot be missed. It is very much like the GNS. Okay, and I said CP maps are generalization of positive linear functionals or states. So it is same kind of thing, and the proof, one can give a proof which is very similar to the GNS. It's a very natural construction, and if this instead of B of G, if you have just C complex numbers, so you can think of it as B of complex numbers, and you do the same kind of thing. You see that you get the same thing. You get a linear map from C to H. That means a vector, right? A linear map from C to H. You see where the 1 gets mapped, so you get one vector H, Z. So this is actually a generalization of the GNS construction. And here too we have the minimality. If you put the span closure of this, the vectors generated by this part, if that is the whole of H, then we have minimality. And the uniqueness theorem still holds, namely that if you have minimality, this triple is unique up to unitary equivalence. Okay? So now the next step, I think, should be obvious. If you have two such CP maps, what should be their distance? Okay, so what is the Bures distance for completely positive maps? It is quite surprising, means because this theory of CP maps has been around for quite some time, and also the Bures distance is very old, actually, the notion. Actually, the Bures defined it for a different context, not just for the purpose of defining a distance, but for some other reason. And later on, it was used by Araki and others in various contexts. It is not forgotten. It was being used, but how come the same notion was not extended to CP maps? Okay, so this happened only recently. So this is the JFA 2008, but they had a result, the same result, I think, few years earlier. They had written it in the quantum information context and had not written it in this form, but then they extended it and put it in this form. So these three authors, Kreshman, Shingman, Warner. So let us see. So the state idea is, of course, same. So you define two CP maps, say you have from A to B of G. Then you take beta of phi1, phi2 as the infimum of norm of v1 minus v2, where we have two common representations. H and pi are same. So, and phi means vi represents phi. Okay? So it's a common representation. You take H and pi and take the infimum, and the infimum over all common representations. So there is the infimum over all H, pi, and v1, v2. Okay? So all things are varying. So infimum over all common representations. So that you take as the distance between phi and phi2. And here also the infimum is attained, and one has lower and upper bounds for beta. Okay? That is their theorem, and it becomes a metric in good cases. Yeah? Pi is a representation. This one. Okay. So phi A is this, and Okay, but before going to the foo for getting to this thing, so I see that there is a thing here that is going from A to B of G. And why did that happen? Because the thing is, we have Stinespring's theorem is of that kind, right? So it is a map from A to B of G, and then V becomes a linear map from G to H. So in that form, it is not a phi is not a CP map from A to another C-star algebra, but it has to be to B of G. So, and these people did extend it another way to for general case from one C-star algebra to another C-star algebra, but then the definition is sort of twisted, and it's not natural like this. It is a so what we want to do, take a different approach. So this Stinespring's theorem, you can put it another way, okay? So where it looks even more like the GNS, okay? So that for that you need this Hilbert C-star modules. So so I am now taking a CP map from A to B, where B is another C-star algebra, and then I say there exists a pair E comma Z, where is a Hilbert AB module. Okay, so this needs some explanation. So since I typed everything just yesterday, I did not type all the details. So this here, E is a Hilbert B module. So in fact, AB module I am saying. What does it mean? It is, E is very much like a Hilbert space, but it's Hilbert C-star module, means the inner products are taking values in B. So originally, when we had a linear functional from A to C, we had got a Hilbert space here. We had got actually a triple. I am contracted it into a pair. So this is replacing, the E is replacing that Hilbert space. It's a Hilbert C-star module. The inner products are now taking values in B. So there is a right action by the Hilbert space, this C-star algebra B. Okay? And there is also a left action by this algebra A. Okay? So this left action is replacing the role of that pi, the representation. The left action. So this means that we have a homomorphism from A to bounded operators on E. Okay? So if you look at the bounded B linear operators on E, so there will be a map from A to, so that notation for that is BAE, adjoint table operators on E. So there will be a homomorphism from A to BAE. So that is the left action. So since I am hiding the left action, so I am just saying that E has a left action, so that representation pi doesn't appear. It is actually there, it is the left action. Okay. So we get a triple like this, and the CP map phi is given by Z A Z. This is the left action. So the A Z, you can think of it as pi A Z, the representation pi of A. So now it is exactly like the GNS. Okay. So the only replacement has been that the inner products are now taking values in this C-star algebra B, and the positivity is in the sense of the positivity of the C-star algebra, not the usual positivity of complex numbers. So phi of A is Z A Z. Okay. So the Stinespring's theorem, in the general case, instead of B of G when there is B, we can put it in this module language, and we also have the minimality in the sense that the span closure of this sorry, I forgot, there should also be B on this right side. Okay, it should not be just one side. A Z B, B from B. Okay, the right action also you should, the module thing, that also you should put. Then the span closure, so that should be E. Okay. Now, okay, I would like to go to that lower and upper bounds for the definition for the Bures distance here is obvious. Once you put in that form, you want to find out the infimum of norm of Z1 minus Z2. So, and then we want to get lower and upper bounds. So here, so as I said, some things are not tied up. So we would like to restrict ourselves to Von-Neumann algebras and the CP maps as normal. Okay. So, so when you have Von-Neumann algebras and So here, you see, there is one technical point here. I have just written span closure. The span closure would normally mean the closure in the norm of this. Okay, E is a Hilbert module, so it has its inner product. So taking values in B, so from the inner product, one can get the norm. Okay, for any vector Z, Z inner product Z is a positive operator. The norm of that as an element of B, the square root of, take the square root, that will be a norm in E. So you can take the span closure in that. But when you have von Neumann algebras, then you need von Neumann modules or self-dual modules. So in there you have to take the closure in strong topology or strong operator topology, that kind of thing. So we are doing that. Okay. So then one can show that beta is a metric. In fact, generally whether beta is a metric or not is still unclear. Even in their paper of these three people, they don't show it in general. So they do show it only when the range is just B of G or some injective von Neumann algebra and things like that. The general case is unclear, but we hope we can sort it out. Okay, and here is the bound, lower and upper bounds. Okay, so you have two CP maps on two from C star. I'm taking von Neumann algebras from A to B, and beta is, this is a lower bound and this is the upper bound. So this CB, that I have to explain. So that is the CB norm. Okay, not the usual norm, but you have to. So say this phi1 or phi2, if you have a map from A to B, you have the associated maps at the matrix level. So look at, say suppose I look at phi1. So it's a map from A to B, then you can sort of ampliate it. So if you take n cross n matrices on A, I can get, by acting just entry-wise, map from MnA to MnB. So take the norm of that. So take the supremum over all n's. So that is the CB norm, the completely bounded norm. Okay, so that you can do for any map from A to B. So, so I am taking here not the usual norm, but the completely bounded norm. So, so you have to go at all matrix levels. And then you have this inequality. So lower bound by this, the upper bound similar to what we had in before. Earlier we did not have any lower bound, but okay. So I'll give a few minutes as to how that goes. Well, maybe first the lower bound. The lower bound is actually a triviality. Means it's not very difficult to get the lower bound. See, you have this beta phi1, phi2, which is the infimum of norm of z1 minus z2. So the norm square you look at of z1 minus z2, then you expand, and then just add and subtract some terms and you will get this. And the point to note here is that I have put CB norms everywhere, but this CB norm get the upper bound. So what is the idea to get the upper bound? So there is a crucial lemma here. So we need to define a couple of things. Okay, the first thing is this. So suppose I have a common representation. Okay, so I have two zi's, phi ia represented like this. So it's a common representation on some module E. Okay, so this is some von Neumann module E where we have representations for both phi1 and phi2. Like last time, there is we always have such common representations because you can take the direct sum. Okay, so this is just the inner product between z1 and z2. So why do we look at this? It is a collection of all such inner products. See, we look at that because see, if you look at if you want to take the infimum of square root of such things. So, but if when you take the inner product, you see that you have phi1 1 and phi2 1 and minus this. So in other words, what I need to look at is the real part of this. Okay, all such things. So the other part goes away. Z1 Z1 and Z2 Z2, they are fixed because of phi1 and phi2. So I need to look at the collection of all such possible inner products. So they are all elements of B, the C star algebra B. So I need to take all possible things like this and then take the real part and then take the infimum over such things. So it is this union which is important. And I define another thing here. Okay, that also needs some explanation. So what is this? So this is a similar thing But when I have two modules, E1 and E2, we define this. So I should have put E1 and E2 here. So, but you see why I have not put E1 and E2. So these are maps from E2 to E1, okay, from one module to another. So both are two-sided modules, so they are bilinear maps. So the maps linear with respect to both left action and right action. Okay, so they are sort of intertwiners. Okay, the crucial lemma is this. Yeah.
That union over E or R.
Over all common representations, all common representation modules. So that is all E where you can represent phi1 and phi2. Okay, all possible modules you can say, because if you cannot represent this, then you don't have this kind of inner product. That's all. You can take it as empty set when you cannot represent it. Okay. The crucial lemma is that you can get this n in another way. You look at this kind of bilinear maps from one to another. So that M phi1 phi2 actually does not depend upon which modules E1 and E2 you take. Okay. So that is the point. So this and once you have that, this M phi1 phi2, that is also equal to this union. So this big union is actually can be got from any two representations E1 and E2 this way, and it's also equal to the n at the direct sum, where E1 and E2, E1 hat, E2 hat are the minimal dilation spaces. You always have the minimal one. You take their direct sum. We know that that is always a common representation. So this n may depend upon E, but this M does not depend upon that. So I should give some idea as to why that happens, why it doesn't depend. As I said, this is something like intertwiner space. This M is a subset of B, in the C-star algebra B, or phenomenon algebra B. Okay. So the point is that suppose I have a well, yeah. Oh, okay. Yeah. So this one. The idea, how do you show that this does not depend upon E1 and E2 hat? So you look at the case where you take the minimal representation space. So E1 hat and E2 hat. So we show that M defined like this is same as the M at the minimal space. For any module, two modules E1 and E2 you take, that is always equal to the corresponding thing for the minimal one. So how do you do that? This is where I need this phenomenon algebras. So see, E1 hat and E2 hat will be sitting inside E1 and E2, because E1 hat, so it has this common representation. No? This Z1 is there in E1, so I can look at the space generated by Z1. So that the minimal space would be sitting inside E1, and I can take the projection onto that. So that is possible. So only in the phenomenon module case. So that is the thing about Hilbert modules. So like in Hilbert spaces, whenever you have a subspace, you can project onto that and have the direct sum decomposition. So that is not possible in general for Hilbert C-star modules. Okay, but it is possible for phenomenon modules. So whenever you have a submodule, which is a phenomenon module, you take the proper closure, then you can decompose the whole space as a direct sum. So, and that is where I need. So this minimal ones, E1 hat and E2 hat are sitting inside this. So you can actually restrict this I to that part, and you can also see a map from E1 hat to E1 and E2 hat to E2. So the natural embeddings. So through conjugation through that, you can shift from one to another. So through that method, we can show that this actually these kind of inner products, which are called intertwiners. So that depends only on the CP maps phi1 and phi2, and not on these representations E1 and E2. So because of that, I can connect the things, and that would be equal to this big union, and is also equal to the case when you take just the minimal dilation space. Okay. So as a corollary, see, as I said, I want to take the infimum over such things by taking the norm and then take the square root. So when I take the infimum, only the real part of this comes, and the real part of this, so these are elements in this n, and that is always attained. You don't have to take the union over all E. So though it looks big, actually it suffices to take the direct sum of this. So the beta is actually attained in E1 hat direct sum E2 hat. Okay. So so I just repeat. So the idea is to go shift from n to m, and once you go to this bilinear maps and m, and it doesn't depend upon E1 and E2, so then one can restrict our attention to just this direct sum. Okay. So then then there are a lot of computations after that, and the way they do get the upper bound is actually to reduce it to the case of the Bures case. You look at the states on the that Feynman algebra and reduce it to the proof of Bures, and the Bures proof, again, it's quite complicated, that compactness, and you also need this Keyfan's minimax principle and this, that. So we have been trying to simplify that proof, and we hope that with this module approach we would get a much simpler proof. But so far we have to restrict to this kind of Feynman modules, and we still are unable to simplify the things. But what we could do is sort of rewrite the whole thing, their proof, in the module language. That we can do. And the other thing what we could do is that so that they give us a conjecture as to whether this beta is attained in all common representations. As I said, this is the case in the Bures case. When you have states or linear functionals, the distance, the metric is attained in all common representations. And we are able to give a counterexample to say that it is not the case for general CP maps. So that was left there as a conjecture, and very simple examples actually in just matrix algebras. We have simple examples to show that it is not attained in all common representations. So the funny thing is that
I thought you said for the Feynman case it is true.
Even for Feynman case it's not true. It is true for states. For linear functionals it is true. Okay. The infimum is attained and is symmetric, but you have to take all things. I didn't say that. The minimum is attained in this minimal direct sum.
What he said is that the Warner's proof he could rework in the language of.
No, but can't you, if the whole thing is a Feynman thing, can't
Yeah.
you put this direct sum, can't you embed this into anything?
No. The funny thing, the kind of examples we have, you see, this E1 hat itself may become a common representation for phi1 and phi2. So then E1 hat direct sum E2 hat will not embed there. Okay. So we have an explicit counterexample to say that this is not the case for all common representations. Okay. The space there to, you see, we have to sort of intertwine, we have to shift the things using this M, okay, this kind of bilinear maps, okay, and that there may not be enough space for that. So when you take in general, okay.
No, so maybe rephrase like this. So in the C star case, can you have a candidate of this E1 hat direct sum E2 hat?
No, that is there.
Particular thing that works for everything.
No, that would work. E1 hat direct sum E2 hat would work. I think even in the C star case, but in the C star case we are still not sure about something. Let us restrict to Feynman algebras. In the Feynman algebra case, E1 hat direct sum E2 hat will definitely do.
The C star case, what is E1 hat?
Yeah, so the span closure, whether you want to take in the just the norm or in the strong norm, that is the only question there. Okay.
So is that C star, is there a bimodule? We take is the norm closure?
Yeah, it would be. It would be a bimodal. There's no problem there. When I take the infimum over all things, the Feynman things would automatically come into picture, because you can take the strong closure even if it was not talking about C star algebras. But it's not clear. Some of the things are not clear for C star algebras. But for Feynman algebras, it's okay. And we also have an example where, yeah, so this is correct. Okay. So where this beta is greater than the usual norm, the square root of the usual norm. So that they didn't have. They had this bound but then it was not clear whether one actually needs the CB norm or not. So we have an example, again an explicit example, where this beta is bigger than the square root of the usual norm, but it's as it should be, it is less than the CB norm. So it's crucial to have the CB norm. And we also have an example, like in the previous thing, as I said, like this. So this inequality shows only for this big union is equal to the case for the direct sum, but what about the general ones? Whether all of them are equal. So that was left open. So this is, for M it is clear, it doesn't depend upon E1 and E2, but for N, whether it depends or not, it was left open. And we have an example to see that it actually matters. Okay. So finally, so that was all working on that. With this, another good result we have is this, what I call rigidity theorem. So here A is equal to B. So I have a CP map from B to B where the beta distance is less than 1. So for example, if the CB norm from phi from this is the identity map. So phi is very close to the identity map. Okay. So if you take the identity map from B to B, the module for that, the representation module for that is just the B itself. Okay. See, B itself is a phenomenon, means it's a phenomenon module where the inner product between B and C is B star C. Okay. So just like C is a Hilbert space, any module here B is also a, means any C star algebra or phenomenon algebra, it automatically becomes a module. It's a sort of trivial module. So the inner product coming from the algebra operation itself. Okay. So inner product between B and C is B star C. So for identity map, that is the GNS space or the Stinespring space. Okay. So what the theorem is saying is that if I have a map which is close to identity, then the module contains a copy of B. Okay. So it cannot be far from that. Means it's a the module. See, that is. I think this is the first result of this kind, as far as I know. And why am I interested in that? So the reason is that the whole idea for me is to extend this Bures distance everything to CP semi groups. And for that, the thing I had to do it was to for map from A to B of G, I need it from one C star algebra to another C star algebra. So for example, phenomenon algebra is also okay. Say B to B. If I have a whole CP semi group, then can we define the distance and things like that? And then phenomenon module. So this is the direct sum, so it is a phenomenon module. Means it's a here everything is in phenomenon module thing. Okay. So I want to talk with the projection onto this and the orthogonal complement that way. See, what this is saying is that there will be a map close to phi, which is a sort of elementary. It is a map of the kind some C star AC, which is dominated by phi. So it gets connected to units, or what we call the central units of a CP semi group. So hoping that this gives you some idea that whenever I have a CP semi group, when it becomes close to identity, then there is something which is dominated by it, so it will give you a unit. Okay. Okay. So here are the references, and well, the Bures original paper, as you could see, it is about entirely different thing, but that comes there. Naraki has used it, and recently there has been a lot of interest in this because of this kind of information disturbance and things like that. And this is the standard reference for Hilbert C star modules, if you want to get introduced to that. And
more questions? There was already interaction during the talk, but any other questions?
Actually, with the second year trait, you get the system result.
Maybe. See, we have not yet tried. We are still trying to set up the phenomenon algebra thing in proper way. I think my feeling is that C star algebra, generally it is not true. That is the feeling, but we have not yet tried properly. So we will try. So the question whether the infimum, where I should take the infimum and how it I'm not sure, but it will take some time. We are trying to get a simpler proof for the phenomena algebra case because the proof what they have is quite roundabout, going back to states and things like that. So
Also, in the one-hour case, is there a good alternative candidate who use this rather than, because there is like a norm for it.
yeah. No, so they have given, they themselves have given another thing, which is by going to 2 by 2 matrices. Okay, so this I have not written it down here. It is you sort of look at phi1 minus phi2. Okay, so then try to extend it to a 2 by 2 map, which is CP. Okay, a usual thing which you see in Paulson's book, and take the infimum of norms there. So using that, one can get a value which is similar to this.
Let's break for lunch. Same place as yesterday.